Next, we are going to talk about the spherical capacitor and how to calculate its capacitance. Again, we will be using Gaussian surface because we're using Gauss law to find the electric field, and then once we find the electric field, we will integrate it to find the potential difference, and then we will use that in the electrical equation for capacitance to figure out the geometrical equation of the capacitance for a spherical capacitor. And so far we have two different equations, one for parallel plate capacitor, the other one is for cylindrical capacitor, and you should be able to see how different they are, and they are also on the equation sheet, so you can get familiar with where they are on the equation sheet. So we will talk about the spherical next. We are, again, it looks very similar or the same as the cross-section of the cylindrical case, but now this is spherical. So we need to kind of remind ourselves that because this Gaussian surface is spherical one, not a cylindrical one. And just like before, the electric field is kind of radially out, and you can see those electric field vectors. Similarly, path of integration is given from negative to positive. Inner surface, sphere radius is A, outer one is B, and we are measuring the electric field at a distance little r. So it's on the Gaussian surface, and once again, inside we have positive charge, and the outside spherical shell has negative, and they are only in the inner surfaces. Okay, they're close to each other because they're both conductors. Okay, so once again, we will find it from C is equal to Q over V. But first we need the electric field. So from the Gauss law, I'm gonna again just simplify a little more. Or that integral E dot dA becomes E times A, and that's equal to enclosed charge, which is simply just Q. We've done that a few times already, so I think this is clear. Q over epsilon naught. And the area is the area of a sphere, so we will write the electric field as Q over, since area of a sphere is 4 pi r squared, we're going to use that in here, so we have 4 pi epsilon naught and then r squared. That's the electric field. And this looks like a point charge equation, right? Because remember the shell theorem, we can condense that at the center as if it was a charge, because we are finding the electric field outside of it. And this is the equation for the electric field. But again, it depends on 1 over r squared, so it is not constant. So in that case, when we do integral, we do it from negative to positive, E dot ds, it becomes again negative E ds as before. We talked about that. So that negative will go away, but once again, we have this definition is still a radial integration, so we're going to replace ds with dr, then we will introduce another negative, so we have a negative that remains, and the electric field given above. So let's put the constants out. 4 pi epsilon naught and q are constant, and that's going from b to a. That's the path integration, and dr over r squared is what we have left with inside. So we just left out this r squared here because that was the only r dependence, and we have it in this integral, and we need to integrate this now. And when you integrate this, you get q over 4 pi epsilon naught first of all. Let's put this down. Oh, it's not what I was. Okay, I'm gonna pull it up a bit and give myself more room. And when you plug in the intervals in, the first one first, and you know that this gives you 1 over r, this integral, so we all have 1 over a minus 1 over b, and there's also a negative sign, so it kind of cancels out with the negative in the front, already taking care of that one. And if you look at this, you can make the denominators the same, so you have again q over 4 pi epsilon naught b minus a divided by a times b. That's the potential. So the only thing left with is C equals to Q over V. And once again, Q's are going to go away and everything will flip because V is at the bottom. So we will have 4 pi epsilon naught A B over B minus A. So now this is the capacitance for a spherical capacitor. Okay, and this is a geometrical equation, and this is in the equation sheet if you take a look at it. Right under this, it says an isolated sphere. What is the capacitance of an isolated sphere? It really, that equation, which is 4 pi epsilon naught r on the equation sheet. So this is, let me just write this for, this is a spherical conductor. And there's also a capacitor for, which is given as 4 pi epsilon naught r, and this is isolated sphere. Okay, so this one, let me use a different color. This one comes from this, if you think about this potential, so I'm going to focus on right here. For an isolated sphere, you don't have the shell. Shell is kind of at infinity. So that, if you go up here, that radius B kind of goes to infinity. Okay, when B goes to infinity here, what happens is this whole thing goes to 0. And A is the radius R. Okay, so this becomes R. And what you see is the potential becomes Q over 4 pi epsilon naught R. And when you plug it in for this Q over V, again, the Q's are going to go away. When you flip it, you get 4 pi epsilon R. And that's where the isolated sphere is coming from, the capacitance value for that isolated sphere. And the next ones are, again, we have a question and then a couple practice questions coming up. And this is where I'm going to end, and then we will talk about the next section. But this section emphasized on finding the capacitance, the geometrical equations for several different types of capacitors.